Okay, so let's look at something that we did at the very beginning of the class at the first unit. We talked about an implication, contrapositive, and its converse, and we looked at statements like if a person is carrying a weapon, then the airport metal detector will ring, or if the airport metal detector rings, then the person is carrying a weapon. And we talked about how those two statements are different from each other, and one can be true when another one can be false. I think I might have also mentioned back then that later on we would talk about it in a little bit more nuanced way by throwing in probabilities, because usually rather than saying if a person is carrying a weapon, then the airport metal detector must ring, you would think about a statement more like if a person is carrying a weapon, then there is a pretty high probability that the metal detector will ring. And say if the airport metal detector rings, then there is such and such probability that the person is carrying a weapon. And this extends to all sorts of implication, all sorts of statements. For example, rather than saying if he's a murderer, then his fingerprints are on the knife, really a better way to think about it is if he is a murderer, then there is a pretty high chance that his fingerprints are on the knife. Whether it's always a murderer leaves fingerprints on the knife, well, I don't know, doesn't seem likely. So how do we mix together logic and probability now, combining many things that we talked about in this course, and make those statements a little bit more precise by using probability? So in statistics, people often use terminology sensitivity of a test and specificity or selectivity of a test. And here's how it comes in. Let event A be that the metal detector rings, and the event B be that the person carries a weapon. So a sensitivity is a percentage of correct positives, sensitivity of a test, which means it's how many times when the how can I say it to make it more correct? So a positive is the person carries a weapon and the metal detector identified it. So it's a probability of the metal detector ringing given that the person carries a weapon. And if the metal detector rings, if the metal detector rings when the person carrying a weapon, that's the true positive. If the metal detector rings when person is not carrying the weapon, that's a false positive. And when it doesn't ring when the person carrying a weapon, that's a false negative. So percentage of correct positives out of all positives, out of all weapons, what percentage did the metal detector detect? That's the sensitivity of the metal detector, sensitivity of the test. So in other scenarios, if there is a test for some kind of disease, then sensitivity of the test is a probability that the test will pick up on the person being sick. It's sensitive to the condition. So the more sensitive test will pick up more people that are sick and will say, oh yes, this person has like Lyme disease or something. But know that this is just one half of the story, because you could have a test that always says yes, you could have a metal detector that always rings, and it would be beautiful. It would have 100% sensitivity. It will, on all the people who carry a weapon, such a metal detector will ring. On all the people that are sick, such a test will say positive. It has a great sensitivity, the test that always says yes, but is it really useful in practice? So for that, we need the notion corresponding to the converse. And this is the notion of specificity or selectivity. And when sensitivity talks about percentage of correct positives, how good the test is identifying a positive when there is a positive. Specificity talks about the percentage of correct negatives. How good is metal detector in not ringing when the person is not carrying a weapon. And in this case, so sensitivity would be probability of A given B, or percentage of number of correct positives over all the positives. Specificity would be the number of correct negatives over all negatives, the probability of not A given not B. So it's a probability that if the person is not sick, then the test is negative. And if you take the contrapositive of it, it's the same as saying probability that the test is negative. If the test is positive, then it must be that the person is sick. What is the probability of that? So again, sensitivity is probability that, let's say, if a person has a weapon, then the detector rings, and a very sensitive detector will ring all the time and be kind of useless. Specificity is if the detector rings, then the person must have a weapon. And this is the same as saying if the person does not have a weapon, then the detector does not ring. And the test that will always say no will have a beautiful 100% specificity. It will never accuse an innocent. But it's going to be about as useful as the test that always says yes and has a beautiful 100% sensitivity. So one important thing here is that sensitivity and specificity are not negations of each other, just like implication and its converse are not negations of each other. You could have very high sensitivity and very low specificity. You could have very high specificity and very low sensitivity. If you're lucky, you could get both good sensitivity and good specificity. So let's look at another example, because this is a little bit of a tangled concept. So again, sensitivity is percentage of correct positives out of all positives. Specificity is percentage of correct negatives out of all negatives. So suppose there are positive and negatives, and I plot them like this. So everything above the blue line is positive and everything below the blue line is negative. And suppose I have a test, which here I've drawn as splitting that square with positives and negatives into the green side and the red side. And the green area is all the cases, pluses, minuses, where the test said is positive, and the red area is all the cases where it said negative. So let event A be that the test came up positive, so that your symbol plus or minus is in the green side, and let event B be that your symbol is a plus. And the blue line is a correct separation. Stuff above the blue line is all pluses, and stuff below the blue line is all minuses. And here, this is just an example. You could think of pluses as sick and minuses as healthy, or you could think pluses as, has a weapon, minuses as doesn't have a weapon, and so on and so forth. So looking at this picture, what would be true positive, false positive, true negative, false negative, sensitivity, specificity of the test? So we have 24 positives and 30 negatives. And here you already see that the number of positives and negatives really can be quite different, and that really doesn't matter. So how many true positives we have, that is positive that the test identified as positive? Well, it's 23 out of 24. We have one false negative. So sensitivity, and here I'm writing it in percentages, even though later on we'll switch and just use fractions, is 23 over 24, and it's 96%. So now what about specificity? How many negatives we have? We have 22 negatives, but on 8 of them, our tests say that they are positives. 8 of the minuses are in the green side. So the specificity of our test, the test that's separating that area into green and red, is 73%. And you could probably see here that the number of pluses and minuses don't have to be the same. There can be the number of true positive, false positives really don't depend on each other. And really, for sensitivity, you only look at real positives, and for specificity, you only look at true negatives, and they're really not that dependent on each other. Okay, so let's now look at this problem, and usually it's stated as a medical test. You could think about something else, but let's do the standard way. And say there is a medical test that checks for a certain disease, Lyme disease or something. Pick the one that you don't mind talking about. And let's say the test has a false positive rate of 3%. So 3% of healthy people who take this test get labeled as sick. And this would mean this is false positive, so we are talking about healthy people. So this would mean that specificity is 97%. So specificity is talking about the negatives, is talking about healthy people. And let's say that this test has a false negative rate of 1%, and this is the sick people that the test doesn't catch, and it makes the test to have sensitivity 99%. 99% of sick people, the test will say, well, yeah, that person has a disease. So now what you really want to know is not how many healthy are labeled as sick and how many sick are labeled as healthy. What you really want to know is that suppose somebody tested positive. What is the chance that this person is sick? So we do have probability of A given B and probability of the complement of A given B and A given complement of B, complement of A given complement of B, and we want to know probability of B given A. The thing is, there is not enough information so far. In order to solve this problem, there is one more important value that we need to know. And this is the value that tells us how common is the disease. Again, this is something that people who haven't had much training in logical and probabilistic reasoning sometimes get scared for. Suppose there is a test that tests for very, very, very rare genetic condition, and it has, let's say, 90% sensitivity, 90% specificity. Somebody got a positive test. You know what? The fact that this is a very, very, very rare genetic condition should really play a role in them thinking about what the chances are that they actually have this condition. So in order to talk about that, we need a very commonly used in AI, in statistics, and on all sorts of places theorem called the Bayes theorem. And what the Bayes theorem tells us is how we can compute probability of B given A, so probability that somebody got a positive test is sick, given other information, in particular probability that a test labels probability of A given B, probability that a sick person gets a positive, plus some other information. And the other information is how often does this disease occur and how often does the test say yes in general on a random person. So you may think, oh no, that's a complicated formula, A's, B's, B's, A's, how in the world am I going to remember it? There is a very easy way to remember it. You only need to remember the definition of conditional probability. So what's conditional probability? Is probability of A given B is probability of both A and B occurred divided by probability of B. We divide by probability of B because we already know that it occurred, so we're kind of making it one in some respect. So how do you use the definition to get Bayes' theorem? So let's write probability of A given B and the probability of B given A using their definition. So in both cases, we have probability of both A and B, and in one case, for A given B is divided by B, and in the other case, for B given A is divided by probability of A. So now let's do this. Both of them have probability of A given B, and let's multiply the first one by probability of B and second one probability of A, and we get two expressions that are both equal to probability of A and B. So we get two expressions that must be equal. So probability of A given B times the probability of B must be equal to probability of B given A times the probability of A. And now we are done. We got our Bayes' theorem. If we have A given B and want to calculate B given A, well, we take this expression, divide through by probability of A, and now we got a formula for probability B given A. If we have probability of B given A and want probability of A given B, we divide by probability of B and again get another instance of Bayes' theorem. So don't try to memorize the Bayes' theorem. It's really hard to keep track of what you're multiplying by, what you're dividing by, but do try to remember what definition of conditional probability is, because you could always get Bayes' theorem out of definition of conditional probability. So you may notice that I wrote the original formula probability of B given A two different ways. In both cases, on the top, in the numerator, it was probability of A given B times probability of B. But in the second part, rather than writing probability of A, I wrote this complicated expression. So let me tell you what this complicated expression is and how it comes up in the calculation. So in this case, so the complicated expression defines what probability of A is. So what was A? Let's say a test came up positive or the metal detector rang. Usually you wouldn't have the number on hand, how often the detector rings, how often the test comes up positive. You might or you might not. More often, you may have probability of A given B, say sensitivity of the test, and probability of A given not B, and also probability of B, which you still need to use in the other places, and probability of not B, which is just 1 minus the probability of B. And what this line says is that probability of event A happening, if there is another way that may or may not happen, is the sum, like in the proof by cases, it's a sum of probability of the event A happening given that B did happen, and probability of event happening given that B did not happen, when each of those are additionally multiplied by the probability of event B happening or not happening. So again, the way to see it is probability of A given B times probability of B is just probability of A and B, and probability of A given not B times probability of not B, it's just a probability of A and not B. Since B either happens or it doesn't, probability of A happening is probability of A and B happening plus probability of A and not B happening. That's how you get this formula. And again, don't try to memorize it, just think where it came from. And really the only thing you need to remember here to rederive it whenever you need it is again that probability of both A and B happening is probability of A given that B happened times the probability of B happening. So let's do an example with the Bayes' theorem. You will have a lot more of them in the lab. So we define that medical test that has false positive rate of 3%, false negative rate of 1%. And now let's add the missing piece of information. it tests for a disease that occurs in 5 out of 1,000 people. And now again we ask a question what the probability that the person who got a positive result on the test is really has that disease. So let's A be event that the test on the person came up positive, and the B an event that the person is sick, and we want to know probability of B that the person is sick given A that the test came up positive. Here are all the relevant numbers from the couple of slides before. Probability of A given B and probability of not A given B. So the first two we get out of knowing the false negative rate, or and the other two we get from knowing the false positive rate. And the probability of B is 0.005, 0.5%. So now let's calculate the probability that the test came positive on a random person. And here's one place where we are going to use the probability of B, because a random person is going to have a disease in only 0.5% fraction of cases. So probability of test coming up positive is probability of test coming up positive and the person is sick, and plus probability of test coming up positive and the person is healthy. And if you plug in the number, it works out to be roughly 0.0348. So in about 3.5% of all tests, they will be positive. Now we are ready to plug things in the Bayes theorem. We have the probability of A, we have probability of B, we have probability of A given B. Plugging them in, we get the probability that somebody is sick given that the test came up positive is about 0.14. So here's kind of the conclusion. If the disease only occurs in 5 out of 1,000 people, and you have a really good test which only has false negative rate of 1% and false positive rate of 3%, if somebody tested positive, they still have a pretty low chance of having the disease, only 14%, little bit over the 14%. It's not like for sure they must be sick. And the main reason why this number is so low is because it's a rare disease, and the chance intuitively of the test making a mistake on a random person, the test coming positive on a random person due to making a mistake, getting a false positive, is much higher than tests coming up positive on a random person because that person is sick. And by the similar argument, if the test came up negative, then the probability that they don't have the disease is very, very, very high. It's like 99.995%. And again, that's because vast majority of people don't have the disease, and the chances that the both person has a disease and that happen to be the case that's false negative is very low. Okay, so this was Bayes' theorem, and you'll see a lot more of it in the lab. And for the next time, let's think about a different puzzle, an old Victorian puzzle. Imagine that in old Victorian England, and men all wearing hats came to an event, and they left their hats at the door at the garderobe. Maybe they went to see an opera and left their hats at the door. And on the way out, the event was running late, they were all in a hurry, the hats all looked pretty much the same. Each picked a random hat and ran out. So here's the question for you. How many men went home with their own hat if each of them picked a random hat on their way out? So think about this fun puzzle.